Welcome to Lesson 23. The second lesson of Module 10 reviews additional design considerations for steel beams. Turning our attention away from shear, we now want to look at the weak axis bending capacity of a steel beam. For W shapes, the calculation of the weak axis bending capacity is much simpler than the strong axis, since lateral torsional buckling does not occur. This is because the cross-section is trying to buckle into the strong axis rather than the weak axis. There is just too much resistance for this to happen. Note that for the plastic section modulus, the Z sub Y is used instead of Z sub X. Now, since there is no lateral torsional buckling for beams bent about the weak axis, this may lead you to believe that designing beams in this fashion would be a good thing. This is not the case. When you look at the difference between the Z sub X and Z sub Y, you find Z sub X is between 3 and 5 times that of Z sub Y. Therefore, even owing for a reduced moment capacity due to lateral torsional buckling, the moment capacity of the x-axis will still be significantly larger than that for the weak axis or y-axis. Note that when considering the shear design in the weak axis, the area of the two flanges would be used. Also, since the flanges are rectangular, a parabolic stress distribution would occur, and a peak value 1.5 times the average shear stress results. However, shear is never a problem with W shapes bent about their weak axis. Now we want to look at the effects of concentrated loads on beams. We will look at 3 effects: web local yielding, web local crippling, and web side sway. Note that the issue is with the web. These provisions are given in Chapter J of the specifications. As with any design, the design strength must exceed the factor design load or demand. Here we will use capital R sub n for the nominal strength. If we do not have sufficient strength, transverse stiffeners or doubler plates can be used to increase the web capacity. While the concentrated load is shown as a point load in the slide, in practice there is always a bearing plate on the flange to help distribute the load. The length of the bearing plate in the direction parallel with the plane of the web is given by the term lowercase l sub b. Shown are the design provisions for the web local yielding. Note that there are 2 equations. The first equation, equation J10-2, is applied when the concentrated load is a distance from the end of the member that is greater than the depth of the member, which is d. This allows the bearing stress to fully spread out on both sides of the load location. Note the 5 in the equation. This is actually 2 times the 2.5 assumed horizontal spread of the bearing stress. The second equation, equation J10-3, is used when the concentrated load is located within the member depth distance from the end of the member. In this situation, the bearing stress can only spread out in one direction, and only a single 2.5 factor is used. In both cases, a reduction factor of 1 is used to arrive at the design strength. Note that a K term appears in the 2 equations for web local yielding. This K term is different from the K term we used in calculating the web shear coefficient C sub V for shear design. For web local yielding, the K term is the dimension from the outside surface of the flange to the end of the fillet or curved portion of the web. This is the location of the critical section for web local yielding, since this is where the bearing stress first meets the minimum web thickness or area. The critical area that is used to resist the bearing force is given as the length of the critical section times the web thickness. Note how the stress can spread out more when the concentrated load is located away from the end of the member. Again, it spreads out 2.5 times for every unit length in the vertical direction. Web local crippling is the second limit state for beam webs and concentrated loads we will look at. Under relatively large compressive forces from concentrated loads, the web of a beam may act like a column and buckle or crimple. Similar to web local yielding, the resistance to web local crippling is reduced at the end of a member due to the free edge. Shown is the formula used to determine the nominal resistance when the concentrated compressive force is located at least a distance of half the section depth away from the end of the member. Note the bearing length term in the equation. For web local crippling, a resistance factor of 0.75 is used, reflecting the increased uncertainty in the calculation of web crippling versus web yielding, which uses a factor of 1. Shown in this slide are the two equations to define the resistance of web local crippling when the concentrated force is located within a distance equal to half the section depth from the end of the member. Note that the ratio of the bearing plate length to the section depth is used to determine which equation is used. The resistance factor is still 0.75. This slide shows all three equations when the value of the modulus elasticity is substituted. If the computed design strength is less than the required strength, the beam need not be resized. Rather, several options are available. One, you can increase the length of the bearing plate. However, you gain only limited strength. A second option is to use web stiffeners. The stiffeners can be either full depth or half length and either single-sided or double-sided depending upon how much additional strength is needed. We will not consider the design of stiffeners in this course. See section J10.8 for additional information. A third option and an alternative to web stiffeners are the use of web doubler plates that are welded flat to the web of the beam. The doubler plate can be either single-sided or on both sides of the beam web. We will not consider the design of web doubler plates in this course. See section J10.9 for additional information. Web side sway buckling can occur in beams that are supported on top of columns. Basically, the beam bends over the top of the column and the top flange goes into compression. This can cause the top flange to buckle sideways and or the top of the column to kick out. The provisions for web side sway buckling are given in section J10.4. The resistance to side sway buckling is a function of the beam's web slenderness and the unbraced length of either beam flange. Side sway can be prevented by properly supporting the flange and column and or providing web stiffeners or doubler plates in the beam at the column location. When designing beams for floor systems, how much the beams deflect is an important design consideration. Deflections are considered a serviceability limit state. Excessive deflections can result in cracking and damage to components of the building. The shaking and vibration that occurs can be unsettling to the occupants of the structure. And excessive vibrations can make a structure unusable for its intended purpose. We have all been in a room of a building where the floor begins to vibrate or shake as someone walks down, say, a nearby hallway. You want this to happen in an operating room of a hospital? The AISC specification does not specifically provide limitations on deflections, but rather it is left up to the engineer to decide. This is because no single set of deflection criteria can be used to cover all different materials, types of structures, and loading that may contribute to deflections. The engineer must select the deflection limitations from other sources. A general rule of thumb for deflection control is limiting the maximum deflection to the span length divided by 360. Note that the length should be in inches, so the deflection is in inches. It is important to note that this limit is for unfactored live load, as we are concerned with how the structure responds to everyday loading. We are generally not concerned with deflections at ultimate or factored loading, because at this point the structure will collapse, and who cares how much a floor beam is deflecting. The International Building Code, or IBC, which is used in most municipalities in the country, provides deflection limits for both unfactored live load and unfactored dead and live load as shown. Steel floor beams can be fabricated with a negative camber that is equal to the dead load deflection. Therefore, we only need to be concerned with live load deflections, and again, they're unfactored. Shown in this slide is the complete table for deflection limits from the International Building Code. Note that the larger the number is in the denominator, the smaller the allowable maximum deflection. There are quite a number of footnotes associated with the IBC deflection limits table, as shown in this slide. Again, there isn't necessarily a one-shoe-fits-all approach to controlling deflections in a structure. This ends Lesson 23 and Module 10.